Greetings, everyone. In this video, we're going to be taking a deep dive into the introduction of NMR, or nuclear magnetic resonance. This is an introduction to NMR. This is not very in depth because as you progress through organic chemistry, you will learn a lot more about NMR. We're going to be mostly focusing on alkane NMR. Alkene, alkyne, although there are a few alkenes and alkynes throughout my practice problems here. But the very nitty-gritty specifics of that is going to be for a later video, as that's more, that's a latter class. I'm hitting the introduction. Same with carboxylic acids. What else? Carbohydrates. Trying to think of the other ones you cover. Yeah, those sorts of things. So I'm, like I said, just trying to hit the basics. And before we tackle the practice problems, there's a few things I want to cover about just what NMR is, and it has to do with the shielding effect of nearby atoms in further extrapolating that further extrapolating that to functional groups and the effect of those things on hydrogens. Okay, so we're talking mostly about HNMR. CNMR is another thing you'll learn, typically in a kind of the second class of the series. And that will be a separate video as well. But right now we're going to focus on proton NMR, H1 NMR. Okay, so first thing we got to talk about is what the heck is all these weird lines right on this graph? Okay, so this is a proton NMR graph, and it's showing the different hydrogens we have in a molecule. And you'll see this one has 2 peaks, this one has a bunch of peaks, and then here's another 2 peak. Okay, so a single peak represented by a straight line, when we're just kind of freehanding it, this is called a singlet. This means that this hydrogen has no immediate neighbors. And what I mean by an immediate neighbor is a hydrogen that is separated by 3 bonds. So here we have 1, 2, 3 bonds away. These hydrogens would affect each other. Okay? But a singlet does not have any of that. So a very common singlet you might see is if you were to have, let's go, I don't want to draw this. Okay. This hydrogen here would be a singlet. Okay. There's a bunch of different singlets you can get. That is just one example I came off of the top of my head. You would likely not see an NMR like that in very introduction proton NMR. But that's something you'll see towards the end of your, kind of introduction to OChem, that series. Okay, so a singlet. This represents, the splitting pattern. That's what we call how many lines there are, the splitting pattern. And then finally, we have what's called the integration number. Okay, so if I said 1 hydrogen above, well, this represents the amount of hydrogens that correspond to this signal. Okay, so here this is a 1. That means it's 1 hydrogen. However, you can have singlets that are 3 or 2 or however you want. A very common 3 one you might see is, let me draw that better. OCH3. Okay, methoxy. So these have no nearest neighbors because hydrogens do not split through with each other through oxygens. Okay, and it's 3 hydrogens have the same exact signal. Okay, right? So think about single bond rotation. These hydrogens can move around. So it's 3 hydrogens represented by 1 signal, and they have no nearest neighbors. Okay, so that would be a singlet. Now, it's important to say that height is not very indicative necessarily of how many hydrogens are represented. We're using the term integration number because it's based off of the integration. So it's the area under the curve. Okay? So I don't have a good example, I don't think. Oh, here's actually a good one. Here's 1 and 1 with completely different heights. But if you were to take the integration, they would be the exact same. Okay. Here's 1, 2 and 4, same exact height, but different integration numbers. Okay, and that's because the area under the curve is different. All right, so that's a singlet. Next, we have a doublet. Okay. This means that however many hydrogens we have here are being split by one other hydrogen. For example, let's say we had an integration number of 3. Go like that. Okay, here's our single hydrogen. And here are our other 2. Okay, so we have 2 hydrogens that have 1 nearest neighbor. That would be a doublet. Okay, triplet means it has 2 nearest neighbors. Oftentimes you'll see triplets. I mean, there's so many different ways, but I'm kind of going off of patterns because you'll see with me if, I talk to you a lot about, how to study for OChem is I base a lot of things off of patterns. The least amount of things you can memorize, the better. Okay, because there's a lot you have to memorize, right? You have to memorize all these reactions, for instance, a secondary haloalkane with a strongly basic good nucleophile, right? What is that going to do? All these things you have to memorize. And so the fewest things to memorize, the better, in my opinion. If you can logic it out, if you can identify patterns, that's going to be a lot easier. Additionally, NMR, there's only so much you can actually memorize. Okay, you can memorize the splitting patterns, the relative chemical shifts, which we're going to talk about in a second. But a lot of this is going to be creativity and identifying these patterns. You can brute force it, but it's a lot harder and it takes a lot more time. Identifying the patterns is going to be your best friend because another beast with organic chemistry is dealing with the time on your exams, okay? Right? They are a lot of questions in a short amount of time. You have to really, really go through them quickly. So if you can save time, that's going to be a big help, at least in my opinion. But anyways, so you have a triplet. Very commonly, you'll see that part of a ethoxy group. So here we have 2 hydrogens. Those are the 2 neighbors here. And here we have our CH3. Okay. And so you'll notice, hey, these guys will form a triplet. These guys will form a doublet. Okay, that's a pattern we're going to talk about pretty soon. But identifying what patterns, right, like I said, going back to the patterns, what patterns you often see together and what functional groups those represent are going to be important. Okay, our next one is going to be a quartet. These have 3 neighbors. So for instance, let's go back to our... I'm going to go like that. Okay. A tertiary carbon, right? Or I guess more a tetrahedral carbon. Okay. With a methyl group attached to it, right? This hydrogen will have a quartet signal, right? Because it's surrounded by 3 other hydrogens. Okay. The reason I'm using oxygens over here is because it's a very easy way to make sure there's no splitting patterns. Okay, after that, we have a quintet. And then you have your sextet, your septet, your octet. I don't remember what 9 is, but typically right about like 6 or 7, instead of seeing sextet, septet, whatnot, you'll just see a multiplet. Okay. And multiplet just means it's a lot. It's a lot of nearby hydrogens. So this one, you could count it. However, most of the time, you'll just see 2M. Okay, it's a multiplet. Okay. And you might also see that with 5 as well. It's kind of dependent on the professor where they draw the line. All right, so now that we understand the splitting patterns of hydrogens, right, it's based off of the nearest hydrogens, we can start talking about how do nearby other atoms affect our signals, right? And I use the oxygen being a very easy way to prevent splitting patterns. And so it may be logical to assume that, okay, well then oxygens don't affect these hydrogens at all. But in reality, that's not true, okay? So a good way we can talk about this is R CH2CH3, aka an ethyl group, versus, we'll put the R group over there, CH2CH3, okay? These will appear at different parts on our graph down here, okay? And funny enough, this question right here is going to pertain to this idea. But before we get into that, let's go through just the general-ish trends of NMR. I'm going to quickly draw the graph, and then I will be right back. Alrighty. I went ahead and finished my diagram. It's not a very exhaustive list, right? You can search up exact values for all these sorts of things. But like I said, my entire point with this is see if you can understand the general patterns, okay? Some professors may ask you to recall very specific numbers, like, hey, what is the exact isolated range for a carboxylic acid, something like that. I doubt it, because it is a range, and these ranges can be affected. In fact, actually, what I've labeled here is fun times. We're going to talk about that, how multiple of these functional groups can affect our hydrogens. But in general, on our kind of zero end, this is the shielded side, meaning there's a lot of electron density right around this hydrogen, okay? It's being very shielded. On the 12 side, the very high side, right, a high number side, it's very de-shielded, okay? Meaning that electron density is going to get pulled away from that hydrogen. Okay, so that's why we tend to see very electronegative things further to the left on our scale. All right, so let's go through this. From about 0 to like 1.5-ish, maybe to 1.3, somewhere in that range. Okay, this is where we're going to see our alkyl hydrogens. Okay, these are going to be mostly our sp3. Right, it's kind of not very fun. It's a pretty boring region, but it is important. But it doesn't really, or it tells us there's not a whole lot going on here. However, if you start to see these creeping up, okay, going a little to the left, as opposed, like if you have a signal here versus a signal, here. You may think the one on the left is probably closer to some electronegative thing, okay? but still, it's the alkyl regions, nothing much. Okay. Then from a little bit less than 2-ish to around 3, this is our allylic region. All right. So these are going to be our alpha hydrogens. So you'll typically find them, especially your alkenes, right? So it's just one hydrogen away. Also, carbonyls, they'll be in this region. There's so many allylic positions out there. These are just the primary ones. Then from about 3 to 4, this is where we start to get to a carbon. So a hydrogen is bonded to a carbon that's directly attached to something that's electronegative. So oftentimes you'll see it like a chlorine, a bromine, an iodine, nitrogen, oxygen, that sort of thing. The one I want to really draw attention to is the oxygen one, okay? So the oxygen, you'll typically see it in this area, okay? And it's a very common thing. In fact, a lot of my practice problems are going to use this, I'm telling you now, because it's a very, very common thing to see in NMR. Okay. Then from about 4 to 5, what I call it the fun times. And this is where you start to see a compounding effect. Okay, so meaning we're probably not going to see a single thing nearby. Instead, we're going to see multiple. Okay, so commonly, you may see this is a 2,4 dicarbonyl, but these dicarbonyls where you have an alpha hydrogen in the middle. Notice, this is very similar to this guy here, right? These two are very, very, very similar, right? All I have to do is put this group right here and we're good, okay? But it's this idea of where you have 2 electronegative things, not just one, 2, actually make a compounding effect on this hydrogen. Okay, so it's going to be further up. Same thing for, let's see, what's a good one? That would be another one. So all these different variations, okay, and that's important to take into account, where if you have something that's way higher than it should be, but you're like, it has to be this hydrogen, this splitting pattern, perhaps there's something else nearby that's forcing it a little bit higher. Okay, so then we have the kind of 5 to 6 range, and these are going to be hydrogens directly attached to your alkenes. Okay. Further up is from about 6 to 8, you have your aromatic hydrogen, so especially those attached to like benzene. Okay, these are going to be pretty high because of kind of the nature of pi bonds and that sort of thing. Pi bonds pull electron density. However, that's a very, very simple answer, and it can get way more complex than that. At least in kind of introductory NMR, you're not expected to know why pi bonds create such a de-shielding effect. Just know that they do exist. Past that, kind of our highest end is going to be your aldehydes and your carboxylic acids. Okay, so aldehydes are somewhere around 9-ish. Carboxylic acids somewhere around 12-ish in that range. Okay, so this is, I mean, like I said, it can go way more in depth of this, and perhaps you need to spend more time on that, but these are the most general ranges, and these are going to be the important patterns to identify. Okay, so now that we have this, let's go through a few problems. All right, so our first one, and I should say all of these are designed not just to show you these patterns of these shifts, but also specific multiple signal patterns, okay? So those multi-signal patterns is what I'm really gonna drive home in this video. All right, so first thing to always do, look at your chemical formula and figure out the degrees of unsaturation. Okay, so the degrees of, I'm going to change my font. Degrees of unsaturation. This tells you how many how many unsaturated things you have in your molecule. Okay? So to do this, what you do is you take 2 times the number of carbons plus 2. Then it's add the number of nitrogens minus the number of halogens and minus the number of H's, all divided by 2. Okay, so I often write it as 2n plus 2 minus H. What do I do? Trying to think back to my exams. Minus X plus N over 2. Okay. However you do the formula, totally fine, as long as you have the correct formula in whatever order that is allowed. Okay. So, for this question, we have 8 carbons plus 2, no halogens, no nitrogens, minus 18. That's 16 plus 2, 18 minus 18 over 2, which is equal to 0 over 2 is 0. Okay, so we have no double bonds. Interesting. All right, so the next thing we can look at is, hey, our IR spectrum. Sometimes you'll be given a few IR points, sometimes not. It's completely dependent on the professor. Sometimes you'll be given the wave numbers, as I've done here. Other times you'll be given an IR spectrum. Other times you'll be given none of that. Okay, for my latter 2 kind of classes in the Introduction OChem series, we were not given an IR. It was just NMR. Sometimes you got the J values, which you'll learn about when you talk about alkene NMR in more detail. But that's all past the scope of what we're talking about today. All right. So we have a peak at 1300. Your peak at 1300 is likely going to be some ether, right? A C double bond O. Something like that. Actually, I'm going to write it like that. Oh, one thing I actually didn't mention here is another splitting pattern you'll see is alcohols. Okay, so alcohols do not appear as the line here like we normally see. Instead, they're going to appear, where is it? Something like this. Okay, so I'm kind of giving you a head that we have an alcohol. But I forgot to mention it. But so notice how it's not like the other ones, right? These are all mostly lines. This one is more of a kind of a broaderish peak. Okay, so that's another thing to look at is what types of peaks you have, right? Not just the splitting patterns, not just where they are, but do you potentially have any outliers such as alcohols? All right. So coming back to this one, let's see what we have here. We have 4 hydrogens that have one neighbor, and it's in the next to electronegative region. And that makes sense. Here we have an oxygen. Okay, so we have 4 hydrogens that are all identical. Well, let's see. So we know it's going to be right next to the oxygen, bind to the oxygen. So we should be able to maybe do like a CH3. And that means we have to have another carbon here with a hydrogen on it to get 4. But then 2 R groups. That doesn't quite work, right? How could we get those to be all identical? Maybe something, well, you need to make sure this doesn't have any splitting patterns, so like that, but then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbon. So it doesn't work. Okay. Well, what's another way we could have 4 identical hydrogens? Well, if we were to have this oxygen, oxygen that looks like that. We don't know what's here. We don't know what's here, but we can see that these 2 hydrogens are exactly identical. Okay. Right, we can rotate this molecule around and we get the exact same molecule. And now we just got to figure out what's on the end. And so let's look at our other signals. We have a 2 with a multiplet, which sometimes you'll be given that. So this one you'll be given 4 doublet, 2 multiplet, 12 doublet. I didn't give them to you because I made sure my peaks were very, very visible. Sometimes they're not very nice. And they're kind of really, really terrible peaks, in which case you might be given the splitting. Okay? But anyways, so we have this 2 multiplet with a 12 doublet. Well, that's very interesting. Okay, we know we have some symmetry here, right? This is divisible by 2. And all of these other integration numbers are all divisible by 2. Okay? So, whenever we see something like this, it's not always the case, but it's likely or possible that we have symmetry in our molecule. So, to prove this or to show this to you, I'm going to divide everything by 2. Okay? Because when we're symmetry, we're going to work with one side. And we have this 1 multiplet to 6 doublet, sorry. A 1 multiplet to a 6 doublet. Or if you want to count, this might be a 1 septet. This is indicative of an isopropyl group. Okay. So we have our hydrogens. As you can see, right, if I rotate this molecule, we get the exact same. So all these orange hydrogens are in the exact same area, exact same chemical environment. And finally, our middle hydrogen here is, I mean, there's nothing else like it. It's just one of them. Okay, but we see this 1 to 6 pattern, where we have 1 hydrogen with a septet or a multiplet and 6 hydrogens in a doublet. Right? This is very, very common of an isopropyl. So this, write it 1 multiplet or as a septet to 6 in a doublet. Right? This is very indicative of an isopropyl. Very, very indicative of an isopropyl. All right, and so what we saw is it's doubled up, right? It's a 2 to 12 instead of a 1 to 6. So is it possible to have 2 of these? Well, let's see. We have 2 ends to our molecule that we've been building here. And we have 2 isopropyl groups. So what if we just combine them together? So what we end up getting is this, where I'm going to go ahead and color code the hydrogens. These 4 are here. We have 2 identical hydrogens here and here. And 12 on the ends of the isopropyls. Okay, and we should be able to go back and make sure our answer makes sense. Let's see. These 4 purple hydrogens are pretty high up. That makes sense. They're next to an oxygen. This multiplet not just the splitting pattern makes sense as we talked about, right, where it's being split by these 6, but also this is decently close to this oxygen, right? We talked about the nearest sort of directly bonded effect of these electronegative atoms, but their proximity to them also matters. Okay, so a closer thing, right, a closer hydrogen to an electronegative group will be further to the left than further away. And we can see that here, right? This hydrogen is not quite in the alkyl range, right? Or it's in the alkyl range, but it's pretty high for an alkyl range. It's not low like this one, which makes sense because this hydrogen is closer to the oxygen than these orange hydrogens. Okay, and then we also can see our splitting pattern makes sense, right? It's a symmetrical molecule. We draw a line down the middle. It's the exact same. Okay, so our next one is a little bit harder. It's got a little bit more going on. And before we talk about this, I want to take a quick tangent down the degrees of unsaturation route. Okay, so if we do our degrees of unsaturation, we have our 2n plus 2 plus n minus x minus h, however we want to do it, divided by 2. So we get, what is this, 22 plus 2 minus 12 over 2, which gives us 24 to 6. I think 12 over 2, which equals to 6. That's pretty high. Okay, so if we were to kind of take a quick tangent, if we have some sort of ring, here's a cyclohexane. Okay, this is 1 degree of unsaturation. Other common 1 degrees of unsaturation in alkene is another 1, right? That's a 1. You may also get carbonyl. It's another common one. Okay. And finally, we can also talk about alkynes, which will have 2 degrees of unsaturation. Okay, but 6 is really darn high. So either we have a lot of alkenes and carbonyls and alkynes in here, or we have a benzene. Okay, benzenes are 1 ring, so 1 degree of unsaturation with 3 alkenes, so 1 plus 3 is 4 degrees of unsaturation. Okay, right? 1 for the ring, 3 for each of the alkenes. 4 in total. Okay, so 6 is pretty darn high. My first thought is, hey, maybe we have a benzene here. Benzene, what's it called? Trying to think. Benzene NMR, HNMR is going to be a little bit further down the line, but I thought this was straightforward enough that we could do this one. Okay? But if we see, hey, we have some hydrogens in the benzene area, right? If we reference our chart, this kind of 8-ish area has a benzene, right? And we see that here. So likely we have some benzene H's. And let's logic this out for a second. We have 4 signals here that correspond to the benzene. Okay, how could we get them split up in a 2 and 2 fashion? Okay, well, if we have 4 signals, because this one is a little too low to be a benzene. Okay, we have 4 signals. That means if we have 6 carbons, the other 2 must be occupied somewhere, right, with some R group. And now we just got to figure out where this R groups go. Okay, so let's try if we have them right next to each other. This is the para position. You don't need to know that. But, well, for later classes you will. But assuming you were for the class that I'm kind of dedicating these video towards. Don't need to know that. But this is the para position where we have one group here and a second group here. Would it be possible to have two identical signals? Well, yes, actually it is. Here and here, here and here. However, there's one caveat to this. And it's that these need to be the exact same group, right? In order for our signals we've laid out to be the exact same. And if we look here, we don't have a lot of doubling up of things. So it's likely not completely symmetrical. So it is possible, and we should keep it in mind, but it's probably not going to be the case. How about let's try this one? Let's see. Assuming these are the exact same, this one will be the same, these two will be the same. However, this one and this one are not going to be the same, right? This one is one away from that group, one away from this group, and this one is 3 carbons away. I guess technically this one's 2 carbons away, 1, 2, but I digress. Okay, so it's not the meta position. So let's try the ortho position. Sorry. Did I say this is the... Did I say that's the para position? Sorry. That is the ortho position. I don't know what I'm doing. As the ortho position, this is the para position. Here's meta. And here's the ortho position. I don't know what I was doing. My brain's tired. I digress. Anyways. Okay. So, if we try... gotta get rid of these. There we go. If we try the para position. Well, let's see. Even if these two were 2 separate groups, right? So we'll call this 1 and 2. You'll notice that these two are identical. Same with these two, right? This one is 1 away from whatever group this is, different group, or 2 carbons away, technically. It's right next door. Same with this one. These two are identical, and they are same distance away from this one, same here. Okay? Now, there's more specific splitting patterns that you'll learn when you start talking about benzene NMR. But this is, like I said, this was a really, really straightforward one. I specifically made it this way. And so I felt it was easy enough to kind of bring into an introduction. Okay? So this means we have sort of a semi-symmetrical benzene in that our 2 groups are going to be para to one another. Okay, so now we just got to figure out what the rest of that is. All right. So the rest of our molecule, let's take a look. Where should we start? Well, here we have some alkyl group. Okay. Here we have something interesting. It's near about 6. Let's see, what's near about 6? Oh, a hydrogen attached to an alkene. Okay. So likely, we're going to have something that looks like that. All right, how about, what's at 12? What's above 12? Well, the only thing that's really that high is either an aldehyde or a carboxylic acid. And carboxylic acids tend to be a lot higher, whereas the aldehydes are near like 9, 10-ish. So here we likely have some carboxylic acid. Okay, we can also take a quick tangent and look at the IR, right? Because we are given it, so might as well use it. And so let's see, at about 3150, that's probably our carboxylic acid, right? is hydroxy, this carboxylic acid. So we'll say the ROH. Let's see, what else is here? Well, 1720, that speaks to me as being a carbonyl. But that's pretty high for a carbonyl. So what could be making that so high? And well, we said it's a carboxylic acid, right? So the carboxylic acid, carbonyl, is going to have a higher peak than just a normal carbonyl because it has that hydroxyl group right next to it. Okay? And then finally, at 1600, this is where we'll see our aromatic. C double bond C's, aka our benzene. So everything we found, right, our DOU, our NMR, and our IR all point to having an aromatic. Okay, some sort of benzene. And typically, you're not going to see a non-benzene aromatic until you get to higher OChem, but that is something to take into account. But likely, we're dealing with a benzene here. Okay. There's a whole bunch of other peaks that we could talk about, but honestly, I don't think they're important. What is important, though, is figuring out, like I said, how these all piece together. So we know we're basing around a benzene. Now we just got to figure out how the rest of this all fits together. Well, let's see. We could try. We can try putting. Let's do. We could maybe do. No. Okay. If we were to put our hydrogen here and make these two our methyl groups, that would make this our carboxylic acid. And while this is a pretty good guess, if we pay attention to these two methyls, they are not actually the same, right? These hydrogens here, you'll notice, are 1, 2, 3 away from this hydrogen. Okay, they're geminal. Well, not these hydrogens are not geminal, but this methyl group and this hydrogen are geminal. This hydrogen and this methyl group are trans. So they're not the same. Okay. So that means it can't be that. Okay. Well, what if we just switch them? Put CH3 here and an H here. Okay, well now we have all of these that are 1, 2, 3, 4 away versus 1, 2, 3, 4 away. Now, cis and trans does actually matter, but I made sure that there was nothing that you didn't require any like kind of higher level OChem knowledge to solve this problem. Specifically made it in this manner. Okay, so as we see here, we don't need to worry about cis and trans and the J constants because they'll be identical. Roughly, give or take. Okay. But now we can see that, hey, our molecule works, right? These two are now identical. Okay. We have a hydrogen that's on our alkene. This alkene is para to the carboxylic acid because there's no other place we can put the carboxylic acid, right? If we switch a methyl group with the carboxylic acid, well, then all of a sudden the methyl groups are different. Okay. Our carboxylic acid is present. We have identical hydrogens, right? These two hydrogens versus these two are the exact same, right? The greens are the same, the pinks are the same, right? And you can prove that they're the exact same distance away. One way you can tell, right? You could flip this or you could flip this area and everything's identical. Okay? And finally, we have 6 alkyl groups that don't have any neighbors, right? It's a singlet. Check here. Yep, these are all singlets. Because 1, 2, 3, 4. Okay? So those hydrogens won't split with one another. Okay? So this one's a little bit more tricky. I don't think you're going to get a benzene one, but it is something to take into account. All right, so let's go to our third one. Once again, we'll always do our degrees of unsaturation. We have 9 times 2 plus 2 minus 16 all over 2, which is what, 24 over 2, which is 2. Okay. Then we see a 3400 with oxygen, likely going to be an alcohol. 1700, that's a carbonyl. Probably not a carboxylic acid, right? Because it's not 1720, it's 1700-ish. And then finally our 1620, that's pretty indicative of a C double bond C. Alrighty. Let's see if our NMR matches that. Oh, here is an interesting peak, right? It's more broad. That's pretty indicative of an alcohol. Then we have something at 6. A singlet at 6. Well, we saw with the previous one, right about this same area is where we found that alkene. So we may have something that looks like that. Okay, and that makes sense. We do match with an alkene here. Okay. Then we have this area. Interesting. So these two are both next to something that's electronegative. Well, we have an alcohol. So that means we have an oxygen mixed in here somewhere. We also have a carbonyl. Okay, so we have probably an allylic hydrogen versus our allylic hydrogen for hydroxyl. So hydroxyl versus carbonyl. Right? That makes sense. We have a carbonyl there that matches our C double bond O. And we have a signal in this area, right? Right about at 3. Maybe a little higher than perhaps we would normally expect for our allylic hydrogens, but not by that much. In fact, we'll see why it's higher a little later. But for now, at least, we have likely a hydroxyl, likely a carbonyl. Which one is which? Well, as we saw, this hydroxyl is going to be higher. So this one is going to be right next to this hydroxyl. It's 2 hydrogens in a triplet, which means it'll have 2 neighbors. Okay, so we're likely going to see something like this. Right? Has 2 neighbors. Okay, how about with the carbonyl? Well, this carbonyl is going to have something that, we don't know what's on this side, but we know it has two hydrogens here. I'm going to do them in a different color. Say dark green. Hydrogens here. Don't know what's there, but we do know there's hydrogens here and here. So that means we should see a 2 and 2 together. Well, hey, 2 and 2, 2 and 2. Interesting. Let's keep that in mind. All right, now we have 4 hydrogens in a quartet, which means they'll have 3 neighbors, and 6 hydrogens in a triplet, which means they'll have 2 neighbors. So we have a 4 to 6. Is there any way we could have 4 identical hydrogens that have 3 neighbors? Well, there's no 3 neighbors here. Wait, what if we have another instance of symmetry? Let's try it. Let's see what happens. It may not be. It may be. Okay, let's divide both of these by 2. And we have a 1 to 3. Okay, so this 1 to 3 sorry, 2 to 3. I was like, well, why is this weird? Okay, this 2 to 3, where this one is a quartet, right? The 2 is a quartet, so I should write this a 2 quartet. It's a 3 and a triplet. This is very indicative of an ethyl group. Okay? And if we have 2 of them, we're making an assumption here that we have 2 of these. It's symmetrical. So we should have 2 ethyl groups that are in the exact same chemical environment. All right, let's see. How are we going to put this all together? Well, here, if we take into account these 2, here's our 2 oxygens. And we know we have an alcohol, so that means this guy is not an ether, it's an alcohol. And we see this same exact pattern, right? Those line up. So likely we have HH, HH. We have our carbonyl here, and now we got to figure out the rest. Okay, now what we need to do, we need to take into account our alkene and our 2 ethyl groups. So let's write them up here. Well, maybe we can use the same thing we did over here, right? Where we had an alkene with 2 identical groups, right? Maybe we can use that same ideology. So perhaps we have something that looks like this. Okay? Because those ethyl groups are in the exact same chemical environment. At least until, right, we're ignoring J values for now. Except there actually wouldn't be any J values for that. We don't need to talk about that. That's later on. Anyways. We have 2 identical groups. Okay. Now can we fit these 2 together? Well, hey, you know what? If I just attach this right here, we have a possible molecule. So let's try that. So we have, actually, I'm just going to rewrite it down here. Okay, we need to attach them like that. we'll do pink. Let's see. Does our answer make sense? We have an alcohol with 2 hydrogens nearby with the correct match. Okay. Then we have this 2 and 2, and these other 2 are right next to a carbonyl. And now we can talk about, right, that kind of nearby effect, where these 2 hydrogens are not just being impacted by the hydroxyl, but also this carbonyl. That's why it's a little bit higher. Same thing with these 2, right? These 2 here are being impacted by the carbonyl, but also this hydroxyl. It's further away, so its effect is going to be a lot less, but it still makes sense of why these are higher than the effects or the typical shifts that we should see. Right? That makes sense. Why they're on the higher end. Okay, and then we have this 2-to-3 ratio with 2 in a quartet to 3 in a triplet, indicative of an ethyl, and these ethyls are in the exact same chemical environment, right, in terms of their hydrogen splitting patterns and how close they are to other functional groups that will shift them over. Right? And finally, notice how these 4 are higher, or I should say to the left more than these guys. Well, that once again makes sense, right? Because these are closer to the alkene, closer in proximity than these hydrogens here. Okay. So it's all making sense. All right. We have one more. So I should have said go ahead and try these all by yourself. At the beginning, I didn't because I was stupid. But if you haven't been trying them by yourself, try it by yourself. Pause the video. But I'm going to start working out through it now. As always, start with the degrees of unsaturation. 6 times 2 plus 2 minus 8. 12, 14, 6, I think. 6 over 2 is equal to 3. Okay, so we have 3 degrees of unsaturation. Let's see. 3,500, once again, very indicative of a hydroxyl. 2,850. That's a little too low to be an sp3 hydrogen. But 2,850 is right where we find aldehydes, which are really, really hard to find on IR. But it's a guess. Okay, it may be an aldehyde, maybe it's something else. I don't know. We'll consult the NMR in a little bit. 2,200. Ooh, that's a new shift we haven't seen on this, practice before. But 2,200 is right about the triple bond region, right? So we have C triple bond N and C triple bond C. So it's one of those two probably, and we don't have a nitrogen in here, so it's probably our alkyne. And then 1,700, that is a C double bond O, and 1,200 is our C single bond O. Okay. All right, so now let's see if this matches. Well, hey, whoa. We have something really high that's not in the 12 range, right? It's right about the 9-ish area. There's our aldehyde. So aldehydes are a lot easier to spot on NMR than IR. Okay. Next, we have a kind of a wide peak. There's our alcohol. And now we have to deal with this. What on earth is happening with those peaks? Well, alkynes are kind of funny, okay? They have a lot of pi electrons in a very, very concentrated area. Okay, that's going to cause a lot of deshielding. So if you see some crazy things and you likely have an alkyne, you have more than 2 degrees or 2 or more degrees of unsaturation, you probably have an alkyne. Okay? So these are indicative of alkynes, which does match our region, right? Our alkyne region, our allylic. Oh, I actually didn't write it. Well, the alkyne is in this area. I am actually sorry. I don't know why I didn't write that. Although technically allylic, it would be there, but oh well. Okay. Well, yeah, that matches up. Okay. At least this one immediately matches up. This one's pretty darn high. But once again, maybe we're considering multiple functional groups. Okay. All right. But that weird splitting pattern combined with the knowledge that, hey, we probably have a triple bond in here tells us these are probably something to do. These are probably allylic to our alkyne. Okay. And then finally, we have 3 hydrogens in a doublet, which means they have 1 neighbor. Okay, so we likely are seeing something like this. Okay. All right, so then we have 2 that are allylic to our alkyne. So we probably are I'm gonna put these 2 on the left because I can. And then this guy, an H, and then we don't know what the rest of these are. Okay. Okay, so then we have an alcohol, which I don't know where that is. But it's also pretty high for an alcohol, right? I mean, I guess this alcohol was also pretty high. It's kind of all over the place. That's why I tend not to say where alcohols are typically found in NMR, because I've seen them all over the place. Let's come back to where that alcohol is. But one thing we can do something with this is aldehyde with 2 neighbors. It's in a triplet. It's very common to see students think that aldehydes do not split because, hey, they think the carbonyl, it doesn't split through that. But it actually does because there's a CH bond. Oh, God, that voice cracked. So now if it's in a triplet, okay, we must have that sort of thing. And look, we have 1, 2, 3. Okay, so they do actually couple through aldehydes. Okay, they do split through aldehydes. Okay, so now we got to figure out the rest of this. Oh, well, hey. Hold on. Here's 2 attached to something, 2 attached to something. Could these 2 and these 2 be the exact same? Because we have a 2 and a 2. Well, let's see. These 2 hydrogens would be right next to a carbonyl. So we'd expect to find them in like the 3-ish region. whoops, drew at the wrong thing. And there we go. We do. We do see 2 hydrogens in this region. And the reason it's a little bit higher, right, because we would normally see it kind of under 3, right? If we, once again, consult this, it's kind of under 3 region. The reason it's above 3 is, once again, we have our alkyne. Okay, so multiple splitting patterns, but this 2 and 2 matches up. So perhaps we have something that looks like this. Okay, we're just putting these together. And we know we have another hydrogen here. And then we don't know what's here and here. Okay. So far, it's making sense. Now we just got to deal with where we have an alcohol, and then finally, our methyl group. Well, hey, 3-1 with 2 attachments. If we choose this one to be 3, here's our 3, our 1, and 2 attachments. So maybe this hydrogen here and this hydrogen here are the same thing, right? Because we have no other single hydrogen, right? This one, that's the one we're thinking about. Alcohols don't do that sort of thing. And the aldehyde, we already said what it's nearby to, right? We already figured that out. So that means this hydrogen and this hydrogen are likely the same thing. Okay, so let's draw that out. I'm going to erase the... Actually, no, I'll keep that. So what we have now... Oh, what color did I use? Green. Okay, then we have our alkyne. Our purple, actually, no, I'm going to put our purple hydrogen here. And then we have our methyl group. And now we just got to figure out what goes here. And we only have one more thing we can work with, and that's our alcohol. And now let's see. Does it make sense that we have an alcohol right next to this single hydrogen? And well, hey, this single hydrogen is way in like the almost 5 range, right? It's like 4.8-ish. That's really high. And that's because it's right next to both an alkyne and an alcohol. Okay. And this methyl group is like at 1.5-ish. So that also is getting pulled slightly up. Right? Slightly higher shift. You shifted to the left. That makes sense because it's decently near a hydroxyl and an alkyne. Okay, so there's all these patterns you can search for, as we've talked about, and there's so many patterns to go over. These are just kind of the main ones I wanted to highlight. All these things you should be looking at when trying to attempt these problems. Right? There's a lot going on. There's a lot of things you have to memorize, but if you can try to memorize patterns instead of specific shifts, because as we talked about, those shifts aren't always helpful. Right? Because there's, as we talked about, right, this compounding effect. Right? Having multiple groups nearby affecting our hydrogens. That's not something you can memorize. That's a conceptual understanding. Right? Because if you try to memorize it, you're going to be stuck for hours upon hours memorizing these things. Okay? As always, I hope you guys are enjoying your studies, are making sure you're eating and sleeping well. Good luck with getting through organic chemistry. And yeah, I'll see you guys next time.